started. I'll start the recording. So today in the next class, we will be discussing differential amplifiers, and similar to the MOSFET cheat sheet, I'll also provide a summary for the differential amplifier, which has already been uploaded on your Canvas, but we'll go through that summary document in Friday's class, depending on how much time permits. Okay. So today we are looking into the details of the differential amplifier. Now, in the last lecture, we have looked into some of the advantages of differential operation. And the major advantage that you see is that if there is any interference from the environment, and that interference is a common mode to both the lines of the differential signal, right? So what does differential mean? That you will have two signals and you'll take the difference between the two. That's what you are essentially going to do. Now, of course, keep in mind that when we are talking about differential signals, we're not only just talking about the difference of signals, but there is a particular property that we are interested in, that the two signals or the two AC signals at the 2 points that we are interested in, let's say point X and point Y, they will have the same common mode level, but the differential signal will be 180-degree phase shifted as compared to each other on those 2 points. So that is the property that we'll be interested in differential signaling. Because if the AC signal is exactly the same, the difference of exactly same AC signals is going to be 0. So that will not make any sense, because you will just amplify 0, which will remain 0 in terms of AC. So that is the reason why you need to have that 180-degree phase difference at the 2 points of interest, so that the difference between the two is going to be double of the individual sine waves. So just keep that in mind when you are talking about differential signaling. We saw the advantages that because the common mode interference affects the two differential lines in the same way. Let's say there is an interference in the environment. The interference does not know which one is my differential signal 1 and which one is my differential signal 2. So it will affect both the signals in the same way through capacitive coupling or through any other modes of coupling. So when you take the difference of the two signals, that interference will go away because it's a common mode. So whatever is common between the two nodes, that will go away if we take the difference. But whatever is 180-degree phase shifted, that will become double. So that's the whole idea of differential signaling. There is another advantage which we just talked about, that differential signaling will increase the maximum achievable voltage swing. So if you think about the single-ended scenario, that you just have this common source amplifier, right? So this is a conventional common source that you have learned in class, that your source is grounded, your output is at the drain terminal, which means that your input is at the gate terminal. So this is your common source, and you have some sort of a signal at the output, let's say an amplified form of the input sine wave. But of course, there is some amount of noise on the power lines. There could be some noise or interference in the environment. That means your sine wave is also going to be noisy. Now, if you take differential signals, let's say Vx looks like this, and Vy is the 180-degree phase shifted version of that. Of course, the noise behaves the same way for both the signals. So if you take the difference, the noise to the most extent it will go away, or the interference to the most extent it will go away, assuming that it will affect both the signals in the same way. But also at the same time, when you take the difference, the overall AC signal amplitude becomes double, right? Because when this is at the maximum, the other AC signal is at its minimum. So if this is plus 1 volt and the other AC signal is minus 1 volt, you have plus 1 minus of minus 1. That means the differential signal is plus 2 volts at the highest point. Similarly, at the minimum point, the differential signal will be minus 2 volt if each of these signals are individually plus 1 and minus 1 volts. Right? So that's another advantage, that it will increase the maximum signal level that you have in your system. Of course, at the same time, you pay the price that you are consuming double the area. Also, you're consuming double the power, because you have two of these branches, whereas in the left side diagram, in the single-ended scenario, you have only one branch. All right. So now if you want to write down what is the maximum output swing, so let's quantify it with math. So let me first clear all of this. So in the above differential circuit, the maximum output swing at either node X or node Y. Those are the individual single-ended nodes in this differential circuit. So let's say either node X or node Y. What is going to be the maximum output swing? Of course, you need to make sure that the transistor stays in saturation. How do you make sure that transistor stays in saturation? That the VDS, or the drop across the transistor, the drain to source voltage of the transistor, that needs to be greater than or equal to V overdrive. So you at least need to have V overdrive amount of voltage across the transistor to make sure it's in saturation. So how much voltage do you have available then? So you do not have V overdrive amount of voltage available across, because you need to have that voltage across the transistor. So how much do you have available across the load? You're going to have VDD minus V overdrive. So if the voltage across the transistor is V1, the voltage across the resistor can only be VDD minus V1. Right? So same thing we are saying, that if the voltage across the transistor is V overdrive, the voltage across the resistor, the maximum voltage across the resistor possible is going to be VDD minus V overdrive, which is VDD minus VGS plus VTH, or if you take the parenthesis, then it's basically VDD minus VGS minus VTH. So that is going to be the maximum output swing at node X or node Y. But if you take into account Vx minus Vy, the maximum amount of swing is twice of that. So twice of VDD minus VGS minus VTH. That is going to be the maximum swing that we have for differential signaling. Now, how do you actually create a differential pair or a differential amplifier? At first, it might seem intuitive that, okay, we just have two of these branches, let's say the left side branch and the right side branch. And yeah, of course, if we are applying V in 1 on the left side branch and V in 2, which is just a 180-degree phase shifted version of V in 1. So if V in 1 looks like this, V in 2 might look like that. And then you have corresponding V out 1 and V out 2. Remember, because this is common source, V out 1 will look something like this. So you have the negative half cycle first and the positive half cycle after that. Because there is always a 180-degree phase shift between the input and output of the common source stage itself. Similarly, for the right side branch, the output might look something like this. And the differential version, that is output 1, V out 1 minus V out 2, which is again will be double the amplitude of the individual V out 1 or V out 2, that is going to be your output. So this might seem like a general solution for a differential circuit. And if you say that, you are not wrong, that it is a differential circuit. But there are some problems in this circuit. What is the major problem? That each of these individual transistors, or let's say the gain of the transistor, which is going to be, let's say, GM times RD for each of the individual branches. Left side branch, it's a common source. So the gain is going to be minus GM times, or GM1 times, let's say, RD. For the right side branch, you can again calculate the gain, which is going to be GM minus GM2 times RD. Right? So what is going to be the overall gain? The overall gain is going to be your V out overall divided by V in overall. So what is going to be your V out, the overall V out? That is going to be V out 1 minus V out 2. So if I just write that down, V out 1 minus V out 2 divided by V in 1 minus V in 2. So my actual input is also twice of V in 1 or V in 2 individually, right? Because I'm applying V in 1 on the left side branch and V in 2 on the right side branch. So I have V out 1 minus V out 2 in my numerator. That's my overall V out. But my overall V in is V in 1 minus V in 2. Now, you know V out 1 is going to be this gain. So whatever gain that is, let's call that AV. So V out 1 is going to be AV times V in 1. And V out 2 is going to be AV times V in 2. Right? Let's see if I can zoom in and write that down better. Yeah. So V out over V in, let me clear this first. That is going to be equal to V out 1 minus V out 2, that's your overall differential output voltage, divided by what is your differential input voltage. That is going to be V in 1 minus V in 2. Which means that if I write V out 1 as the individual gain of the left side branch, which is AV times V in 1, and AV is just GM times RD, or minus GM times RD because it's a common source. So AV times V in 1 minus AV times V in 2. Why both the gains are equal? Because if we assume the GM of the two transistors are equal and the resistances on the two branches are equal, then the gains will also be equal because GMRD will be equal for left side and right side because they are identical. So AV2 or AV times V in 2 divided by V in 1 minus V in 2. Now, of course, you can take AV common in the numerator for both the two terms in the numerator. So you'll have AV times V in 1 minus V in 2, and in the denominator, you have V in 1 minus V in 2. That means the gain is just AV. So it's same as the gain that you had in the single-ended scenario. The gain does not change. So if you have a single-ended common source amplifier, and the gain for that is AV, which is GM times RD of that common source amplifier, the gain of the differential version it will also remain AV. The gain does not change because your input becomes double, your output also becomes double. That's the only difference. So assuming that the gain is not a function of that amplitude, which again may or may not be the correct assumption depending on the application or depending on the circuit that you have built. But in general, let's say you can assume that the gain is not a function of the amplitude, and in that case, your gain remains constant. All right. So what is the other assumption that we made here? That the gain of the left side branch and the gain of the right side branch are exactly equal. And only in that case, you can take that quantity common, right? So why or can it be a scenario that the gain of the left side branch and the right side branch are not equal? Of course, it can, because what is the gain? Gain is going to be GM times RD. So RD is this term. Let's say there would always be some amount of difference in the resistances, but let's just say that the resistance is equal. You bought two resistors from the market, which are relatively close to each other, and you can assume that they are similar. However, what is GM of the transistor? GM of the transistor is beta times V overdrive. So again, beta is a factor that can change with process because the two transistors, even though you try to make them exactly similar, they may not be exactly similar. On the other hand, V overdrive, that's the overdrive voltage of the transistor, that depends on VGS minus VT, right? V overdrive is just the DC quantity of VGS minus VT. So we are not even talking about any AC over here, right? V overdrive is VGS minus VT, and both of them are DC terms. So now, depending on where your common mode is, so let's say I apply a signal like this on V in 1 and another signal like this on V in 2. However, your gain, how much gain you will have at the output, that will depend on the common mode level of your input, right? It's not a fixed number. Let's say I want a fixed gain of 10. I cannot achieve that because my common mode voltage, if that keeps on changing, or if I change my common mode voltage, for example, you might want to have a common mode voltage of 1 volt, and he might want to have a common mode voltage of 2 volts. You'll see different amount of gains because your VGS minus VT will be different as that common mode voltage or gate to source voltage is different. What is common mode voltage? Common mode voltage is the common mode level of this sine. And of course, that cannot be 0 because if that is 0, then the VGS across this transistor or the VGS across that transistor is going to be 0. Right? Gate is at 0, source is at 0, that means VGS is at 0, that means transistor is off. So that cannot happen. You need to have a VGS which is more than the threshold voltage. So you have to have a V overdrive that is higher than 0. And that's what we know from DC analysis of transistors, that for the transistor to be on, the V overdrive needs to be greater than 0. However, how much greater than 0, that determines what is going to be your gain. And you may not like that because Yeah, I mean, in applications, it is possible that the common mode level keeps on changing. That signal may be coming from the output of another stage, but you do not have any control, and so on, right? So that output level of another stage might be changing, and because of that, the common mode level of your amplifier stage will be changing, and because of that, the gain of your amplifier will keep on changing. So that's a scenario that the designer generally don't like. So if I give you a problem of finding out the output voltage given an input voltage, you'd like to have the gain constant. If the gain is not constant, things don't work well. But that will be a problem in this case. So what do we do? How do we make sure that my GM, what is the reason or what is the cause of that problem? The cause is that my GM keeps on changing as a function of the common mode input DC level of V1 and V2, which is just the DC voltage of VGS. So my GM is a function of VGS. If I can make, and that is because I'm using this formula over here, beta times VOV, and VOV is changing. Now, somehow, if I can make GM independent of my V overdrive, then that problem will be solved. And we can do that by connecting a current source at the bottom. So just connect the source voltages together of M1 and M2 and connect a current source over here. Why are we saying that it will solve the problem? Because you have a current over here. If the left side branch and the right side branch are identical, let's say my common mode level changes, but the common mode, because it is common mode, it is common for both the inputs. Right? That is the definition of common mode. That my common mode changing means the DC level of V1 and the DC level of V2 are changing. So if this is 1 volt, this is also 1 volt, but then that can change to, let's say, 2 volts, or let's say 2 volts over here. And on the right side also, it will then change to 2 volts. So my common mode is changing, but it is still common. If it is different, then it does not remain a common mode. And that was a problem in the previous case because that would have changed the gate to source voltage of the M1 transistor and the M2 transistor. And then the GM times RD, or the gain of the differential amplifier, would change. However, if we connect a current source like this, what is the difference in that case? Your current source has to draw a particular fixed amount of current because that's the definition of a current source, that the current remains constant no matter what. Right? As long as it is a current source, the current remains constant. Now, you might ask that when does it remain a current source? Of course, then I'll go back to the actual implementation of the current source and say that, yeah, this current source is implemented using a MOSFET. And you need to make sure that the MOSFET, the VDS of the MOSFET is again higher than the V overdrive, so that you are in this region of VDS versus ID curve for that MOSFET. You want to be in the region when ID is constant. That is, the transistor is in saturation. So that's how that current source is implemented. And you already have seen that how to implement the current source or current mirrors. Now, having said that, you might also say that, okay, I might have a channel length modulation effect. And one way to reduce the channel length modulation effect is to increase the length of the transistor. If you increase the length of the transistor, what is channel length modulation? The channel length modulation arises from the fact that you have a transistor, you have the source region and the drain region. So let's say this is my source and this is my drain. And then you have a channel in between. Why channel length modulation happens? Because the channel, depending on the drain to source voltage, can become triangular instead of a rectangular channel. Remember what we discussed during the physics of MOSFET when we were studying the physics of MOSFET? That instead of the channel remaining a rectangular channel, it can become triangular and there could be a pinch-off point, and that pinch-off point moves towards left as the drain to source voltage is changed. Right? That's what we discussed when we were studying MOSFETs for the first time. But why would this? So let's say your length is very large. So supposedly, let's say you have let's just assume an extreme case. Let's say you have a 1 mile long transistor. Let's say the length is 1 mile. Now, by changing the drain to source voltage, you'll basically change the length of the channel or that pinch-off point only by, let's say, a few nanometers or micrometers. And that does not even count because your length is so large, your length is as large as a mile. So if your length of the transistor is large, any kind of channel length modulation effect will be very small as compared to the original length. So how does it matter if I change a micrometer in a mile-long transistor? If I change a micrometer in a 10 micrometer long transistor, then it matters. Again, if I change a micrometer in a 100 micrometer long transistor, it matters less. Right? It's just 1%. Then, so you can just get the drift, right, like that, right? So if the length of the transistor is large, the channel length modulation or the change in the length, effective length, that effect of that becomes smaller and smaller. So if you have a larger length for the transistor, then the channel length modulation will be less severe, and then this curve will be more or less parallel to the x-axis. So that is one way to make sure that the channel length modulation is small in terms of the number. So there are ways to actually make sure that this current is constant. So let's say we have made sure that the current is as constant as we can make it. So, and let's just assume the value of that current is, I don't know, let's say 1 milliampere. Now, if this current is 1 milliampere, and if the left side branch and the right side branch is exactly identical, the common mode might be going up and down. This V1, the DC level of V1 and DC level of V2, that might be going up and down, but as long as they are going up and down at the same time, so that it remains common mode, again, just from the definition, then you can still say that the left side and right side are still identical. And if the left side and right side are exactly identical, then half of this 1 milliampere current will flow on the left side branch, and half of that will flow on the right side branch. So you'll have 0.5 milliampere on the left side branch and 0.5 milliampere on the right side branch. So what does that tell us? That says that now if I want to calculate the GM, if I want to calculate the GM of, let's say, transistor M1 or transistor M2, you can always apply any of those three formulas for GM. Remember that GM is equal to beta times VOV or K times VOV. GM can also be written in terms of twice beta times ID. It can also be written in the form of twice ID over VOV. Now, in the previous slide, because my current was not constant, as my DC level kept on moving up and down, my currents will not be constant. But in this case, my currents in the two branches are constant. On the other hand, the overdrive or the VGS of the transistors will not be constant as that gate to source voltage level change. Right? So because my current is constant, it's better to use this second formula for the GM, because you know the current, which is going to be constant as the left side and right side are identical, and you know that value very well because you know the value of this current source's current. So if you use this second formula, your GM, which is square root of twice beta times ID, that is going to be a constant number. And you know that because, let's say, you know the beta of the transistors, and you already know what is the current flowing through those transistors. Now, you might ask that, is there a fallacy that, okay, if I use beta times VOV, then I said that, yeah, my gate level, the gate voltage can go up and down because of, let's say, some challenges in the design, or because of the fact that these might be coming from the output of another stage where you may not have as much control as you want. So this level can keep on changing, which means if I use GM equal to beta times VOV, does that mean my GM keeps on changing? On the other hand, if I use the second formula where its ID is a constant, then that means GM is a constant. So is there a fallacy? Does GM change, or does GM, I mean, the fact that GM changes or does not change should not depend on which formula I use. Right? It's just a formula, but the physical phenomena should be same. So what really happens is that as your gate voltage moves up or down, the source voltage of that transistor also will move up and down in the same manner, exactly the same manner, so that the gate to source voltage remains a constant. The gate to source voltage will remain a constant, That means V overdrive will become a constant. Even though the gate voltage is moving up and down, the source voltage also moves up and down in the same manner so that VGS becomes a constant. And that has to happen because we said that the current is constant, right? Current is constant in the two branch. What is current? Current is beta times V overdrive squared or beta over 2 times V overdrive squared. So ID, that is the current in the individual stages, that is equal to beta over 2 times V overdrive squared. So if I'm saying my ID is constant, my V overdrive has to be a constant. And if V overdrive is a constant, the first formula also gives you a constant number. It's just that, yeah, you may not know what your V overdrive exactly is because you may not know what is the voltage at this point. But as long as you know ID, you can use the second formula to find out GM, and V overdrive will match to that. So it's not that because we are using the second formula, the GM is becoming constant. GM is becoming a constant, whichever formula you use. The way it is becoming a constant is that even though gate moves up and down, source also moves up and down in the same manner. So that is the biggest advantage of this circuit as compared to the previous one where you did not have the current source. So the differential pair incorporates this current source ISS to make ID1 plus ID2 or even the individual transistors independent of V in CM. So whatever common mode voltage you have in V, that common mode voltage does not matter anymore because you have a fixed amount of current source. But of course, you need to make sure that the common mode does not go to the extremes. Let's say it should not become VDD or it should not become 0. Because in those cases, some of your transistors might go out of saturation. And as soon as transistors go out of saturation, you cannot use any concept that we learned in this class. Right? The transistor needs to be in saturation. And the fact that the transistor needs to be in saturation, that will pose some limitations on how much the common mode can change. And that will be called input common mode range. So in a few lectures, we will be learning how to actually design an op-amp or what is there inside an op-amp. And there would be a parameter or a specification of the op-amp, which will be called input common mode range. That means how much does the input can vary, the input common mode can vary before the transistors start going out of saturation. All right. So if you want to do a qualitative analysis of this basic differential pair, how does it look like? So when your V in 1 is much more negative than V in 2, let's just say that your you have a difference in terms of the voltage level. Let's not go into the details of whether we are applying AC voltage or DC voltage or how does the input common mode look like, what is the signal swing of the AC. Let's not go into all those details right now. Let's make things simple. That, okay, you have at time t equal to some time instant, let's say t1, you have a voltage at V in 1, you have a single voltage at V in 1, and you have a single voltage in V in 2. Let's just say that the value of V in 1 is lower than V in 2. Let's not go into AC or DC. Let's just say that the value of voltage V in 1 is lower than the value of voltage V in 2. And that's why we are saying V in 1 is more negative than V in 2. In that case, M1 is off because this voltage is lower. And let's say it is so low that the M1 transistor is off. But because Vin is high, the M1 transistor is on. And all the current that is flowing here, because if this transistor goes off, there cannot be any current flowing from top to bottom on the left side branch. So even though we said that half of the current will flow on the left side and half of the current will flow on the right side, that will be applicable only in the scenario when both transistors are on. That is, you have set your common mode levels in a way that both transistors are on, but there is a small amount of AC on top of both. Only in that case, the same amount of current flows in the left side branch or the right side branch. But if you have gone to the extremes, so right now we are just talking about the extremes for now. Let's say you have a V in voltage, which is very, very low, very close to zero. And you have a V in 2 voltage, which is very, very high, which is close to your VDD. In that case, your M1 transistor is likely to be off and your M2 transistor is likely to be on. So if the transistor is off, there cannot be any current through it. If the transistor is on, there would be current through it. So in that case, this ISS current, the entire current will flow only through the right side branch. There will be no current on the left side branch because the transistor M1 is off, as your V1 is very, very negative. Okay. So your ID2 is going to be ISS. Vout1, how much will be Vout1? This voltage over here, the left side branch's output voltage. Because there is no current, there will be no voltage drop across the RD1 transistor. So what is the voltage on the top of the RD1 transistor? It's VDD. Because there is no voltage drop, as there is no current, so the bottom of the transistor RD1 will also be at VDD. So Vout1 will be equal to VDD. How much will be Vout2? Vout2 is the output in the second branch, the right side branch. That is going to be VDD minus RD times ISS. That's just Ohm's law. That you have VDD voltage here, you have ISS amount of current flowing through the right side branch. So ISS times RD2 is the drop across RD2. You subtract that from VDD, you get Vout2. Now, as your V in 1 is brought closer to V in 2, let's say I'm trying to make both of them equal, then M1 gradually turns on and it will start drawing a fraction of that ISS current that will flow through RD1 as well, and it will start lowering Vout1. Initially, Vout1 was at VDD, but now it will start becoming lower as this M1 transistor is turning on. So since your ID1 plus ID2 equal to ISS, and ISS is a constant current source, if ID1 is increasing, ID2 has to reduce. The total amount of current has to remain constant because the current source makes it constant. So if the current through the left side branch is increasing, then the current through the right side branch has to reduce. And if your current through the right side branch is reducing, the voltage drop across RD2 is reducing. That means Vout2, that DC voltage at Vout2, that keeps on increasing. Now, when V in 1 becomes equal to V in 2, when both these two voltages are equal, V in 1 is equal to V in 2. Let me clear all of this to make things easier to understand. If V in 1 equal to V in 2, then I say that the left side branch and the right side branch are exactly identical. Because unless the input voltages are identical, the overall behavior of the circuit may not be identical, right? It will not be identical, in fact. So only when V in 1 equal to V in 2, your branches will be exactly identical. So the currents flowing through the left side branch will be identical to the current flowing through the right side branch. And the total addition of those two currents will be equal to ISS. That means each of these currents will be ISS over 2. And that is the reason why in that situation, your Vout1 equal to Vout2, because they're identical, the output voltages will also be identical. And how much will that be? That is going to be VDD minus RD times ISS over 2. Because ISS over 2 times current is flowing through each of these branches. So ISS over 2 here and ISS over 2 here. So voltage drop across each of those resistors is going to be RD times ISS over 2. And that is why the Vout for both of them are going to be equal to the same number, which is VDD minus RD ISS over 2. And that is going to be your output common mode level that you want to have. That my input common mode level makes, what does that mean? That my V in 1 equal to V in 2 in terms of DC. My output common mode DC levels is going to be VDD minus RD ISS over 2. Now I'm going to put a AC on top of V in 1 and V in 2, and that AC signal will be differential. That means 180-degree phase shifted versions of each other. And then I'll take a look at what is going to be my Vout1 and Vout2 in terms of AC. And that is just going to be the gain, the individual gain of the left side or the right side branch multiplied with the overall input. Okay. So that's how basically the differential pair works. And this is just a graphical representation of what we just said. That if I plot on the x-axis V in 1 minus V in 2, okay, and I'm plotting both Vout1 and Vout2 over here with these these solid lines. If V1 minus V2 is very much negative, if V1 minus V2 is very much negative, that means my V1 is much smaller than my V2 in the extreme scenarios. Then there is no current on the left side branch. Again, let's go back to the picture once again for clarity. My V1 minus V2 is very much negative. So there is no current on the left side branch. That means V out 1 will be equal to VDD. And V out 2 will be equal to VDD minus RDISS. As V1 becomes closer to V into, at some point, my V out 1 will be equal to V out 2 when V1 equal to V into, and then V out 1 will be equal to V out 2, which is equal to VDD minus RDISS over 2. And then if you keep on increasing your V1 even more as compared to V into, there would be a point when V into will become very much negative as compared to V1. That means that the right side branch will turn off. So V out 2 will be equal to VDD in that case, if the right side branch turns off, whereas V out 1 will become equal to VDD minus RDISS, and all the current will flow through the left side branch. So that is what we are showing graphically in the next diagram. That when V1 minus V into is negative, that is over here, your V out 1 is equal to VDD, your V out 2 is equal to VDD minus RDISS. When V1 minus V into becomes 0, that is when we have exactly identical voltages at the gates of the two branches, then your V out 1 is equal to V out 2, and that is equal to VDD minus RDISS over 2. That's this line. And then if you, as you start going towards more and more on the right, your V1 minus V2 becomes extremely positive, and then your V out 1 goes down to VDD minus RDISS, and V out 2 goes up to VDD. And if you want to plot V out 1 minus V out 2, of course, on the leftmost side, it's plus RDISS. On the rightmost side, it will become minus RDISS. All right. Now, if you want to see the common mode behavior, or let's say I have, so that is in the scenario when I do not have the same common mode. So this plot and this plot is talking about the extremes, that if I do not have the same common mode, what happens? If V1 minus V2 is not same, what happens? But ideally, I want to have V1 equal to V2. I want to have the same common mode. That's why I'm calling it a common mode. That's why for all practical purposes, you will be at this point. You first bias your transistors in this point, or make sure that your V1 equal to V2 in terms of DC levels, and then only will start applying AC. So for all practical scenarios, you are interested in only in this point. Now let's say that point moves up and down. So how would that look like? That, okay, I have this point as VDD minus RD times ISS over 2. That's the crossover point of the two V out ones. And at that point, your V1 minus V2 is equal to 0. So let's say my V1 minus V2 is equal to 0. But my common mode point moves up and down. That is, they're same, but they're moving up and down simultaneously at the same time. How does that look like? Or how does the behavior of the circuit looks like in that case? So let's say this is my differential amplifier. I have V in CM, common mode V in connected to both of the inputs. I have V out 1 and V out 2. And I'm representing, instead of a current source, I'm just representing it with a MOSFET with the gate connected to a bias. That is, you're making sure that the transistor is in saturation. And in saturation, let's say the transistor behaves like a current source. Okay. So in that case, if I'm going to plot ID1 and ID2 with respect to my V in CM, I'm going to plot my ID1 and ID2. Now, of course, because before I apply a V in CM, which is more than the threshold voltage of the transistor, before I do that, the transistor is not even on. Right? So both the transistors will be off if my V in CM is 0. If the common mode voltage, if the gate voltage of the MOSFET is 0, these are NMOSes. If the gate voltage are not even crossing the threshold voltage, or gate to source voltage is not even crossing the threshold voltage, the transistors are off. If the transistors are off, the current ID1 or ID2, so the left side branch or the right side branch, both of those currents are zero. And that is just another way of saying that I have an open circuit here. Even though I have a current source at the bottom, I have an open circuit at M1 and I have an open circuit at M2. So the circuit is broken. It's not even connected to VDD. Right? That is why there would be no current flow in the left side branch or right side branch if the transistors are off. So if you are, unless you reach threshold voltage, you'll see no current at all. Then you are going to try to find out whether my VDS is going to be whether my VDS is going to be higher than the V overdrive or not. And that will mean whether my transistors are in saturation or not. If the transistors are not in saturation, they don't behave like current sources. So if my input common mode voltage is higher than the threshold voltage, but it is lower than VGS1 plus VGS3 minus VT3. What is VGS3 minus VT3? That's the overdrive of transistor M3, which is this one. The overdrive of transistor M3 is VGS minus VT of 3, right? And that V overdrive is the minimum VDS that you need to have across M3 to make sure M3 is in saturation. Because VDS needs to be higher than V overdrive. So V overdrive is the minimum VDS of M3 to make sure M3 is in saturation. And if that's the minimum VDS, you have a minimum voltage at point P, which needs to be equal to V overdrive of 3, for the VGS, like that becomes the source voltage of either transistor M1 or transistor M2. The point P is the source voltage of transistor M1 and transistor M2, right? And that voltage of point P has a minimum. It needs to be equal to V overdrive of 3 to make sure the bottom transistor is in saturation. So that means until and unless your source voltage over here reaches V overdrive of 3, transistors are not in saturation. So what is going to be the gate voltage in that case? The gate voltage is going to be the VGS, the gate to source voltage of transistor M1, plus the source to or the drain to source voltage of transistor M3. That is the total V in Cm. That there is a voltage drop from input point to the point P, and then there is another voltage drop from point P to point ground. The addition of those two voltages, one is VGS1 and the other one is VGS3 minus VT3. These are the two voltages that we just talked about. The addition of the two voltages, if my V in Cm is higher than that, then only I ensure that my transistors are in saturation, or this transistor M3 is in saturation. Before that, the transistor M3 is not in saturation. So only after that transistor M3 goes into saturation, you see this constant ID current for both these branches. Before that, you will not see that constant ID current because the transistors are not in saturation. Similarly, you can analyze what is going to be the voltage at point P, what is going to be your Vout1 minus Vout2, and you'll see that all of that depends on the fact that you just need to ensure that your transistors are in saturation. So when we actually solve the op-amp related problem, we'll see how we are going to use the ICMR specification, that's the input common mode range specification, to make sure that the transistors are in saturation. We'll do that and we'll solve the problem in the class, preferably by next week. But that's why we are going to use all these concepts, that you need to make sure that the transistor is in saturation. That's it. Something that we had learned in the very beginning of MOSFET analysis. All right. So that's all there in the next few slides, which is actually talking about how you make sure that the transistors are in saturation. But it's easier to understand that from a problem. So we'll look into that when we actually solve the op-amp design problem in next week. But before we go there, we need to also understand how to find out the gain of the MOSFET. Right? Finding out the DC voltages and making sure that the transistor is in saturation, that's the easy part. Right? That's what you need to ensure first before you can even start analyzing the small signal or start analyzing the AC or the gain of the MOSFET. So gain can be analyzed from small signal analysis, whereas biasing can be analyzed from DC analysis or large signal analysis of the MOSFET. So we'll take a look at the small signal analysis. The biasing is something that is easy to take care of, and it will be much more clearer when you take a look at that example. So now we assume that the biasing has been taken care of. Biasing has been done. Transistors are in saturation. We only want to know what is the gain of the differential amplifier using the small signal analysis. And that's why you see that the first assumption is that M1 and M2 are in saturation. Similarly, this current source, whatever transistor that is, that's also in saturation. We have to ensure that. And then we apply these small signal inputs V1 and V2 on top of the common mode DC that we had. So you had some common mode DC, which has to be non-zero, as we had seen earlier, like a few slides back. If I draw that curve once again, so what we are drawing is the ID current, ID1 or ID2. And we saw that if V in CM, if V in common mode, we are not even talking about the AC input. If the common mode at the input, if that is not up to a certain level, let's say this point, which will be equal to VGS of 1 plus V overdrive of 3, or V overdrive of the current source over here. So V overdrive of 3 is the minimum voltage that you need across this current source, or VDS of that transistor. And VGS of 1 is basically the voltage drop from the gate to this midpoint, which we called the point P in the previous diagram. So the input common mode has to be a combination of these two, because this is the voltage. If you follow KVL around the loop, that input common mode voltage is equal to the voltage drop across M1, gate to source, and the voltage drop across this current source, which needs to be V overdrive of 3. So unless your input common mode is higher than VGS1 plus V overdrive of 3, the tail transistor or this bottom transistor is not in saturation. And in that case, you cannot even do the small signal analysis or the AC analysis, because the transistor will not be in saturation. So assuming that those transistors are in saturation and your V in common mode is at a level that every transistor in the circuit is in saturation, now you'll apply the small signal, and the small signal has to be differential. So it needs to be 180-degree phase shifted version of each other. So this differential gain, V out 1 minus V out 2 divided by V in 1 minus V in 2, that's what we want to find out through this small signal analysis. Now, there could be two different ways that we can do the small signal analysis. One is using superposition principle. So there we will look at both of these methods. Method 1 will be superposition, and method 2 is going to be something called a half circuit method. Now, we'll look into both of these methods in detail in the next lecture. But in very brief, what superposition is that instead of applying both the signals at the same time, you'll just apply only one input signal at a time and ground the other one. The basic superposition principle that you learned in 3111, for example. And you'll analyze what is the effect of that one source, one input source, separately. Then you'll analyze what is the effect of the other input source separately, and then add the two effects. That's what we're going to do in superposition principle. And using half circuit, we'll learn something very interesting. That in half circuit is that if you have a very symmetric circuit, if the left side is exactly symmetric as the right side, you can actually analyze only half of it, either the left side or the right side, and the overall analysis will be same as the half circuit analysis. Now, the half circuit analysis is something that you have done already. Half circuit is just the common source amplifier. So you already know what is going to be the gain of the differential amplifier. That's going to be GM times RL. So we'll look at both of these analyses in the next lecture, one based on superposition, one based on half circuit analysis. So let's stop here, and we'll continue on Friday.